Okay, hey everyone. So today we'll do the chemistry revision sheet. That's what you came here for. So let's start off. The first question is 3 grams of ethane were burnt and heat capacity 25 kilojoules. And they say calculate heat combustion per mole of ethane. So obviously heat combustion per mole of ethane. So it gives you a general idea of energy per mole. So you can just work off that. So here you have joules, so that's energy, and then you have to multiply it with Celsius to get rid of this. So it becomes 25 kilojoules times 5 over number of moles. Now 3 grams of ethane, so mass over molar mass, so 3 divided by ethane is C2H6, so that's 30. So it ends up being 1250 kilojoules. Now it's exothermic, so there's a negative, and then you account for significant figures, and then you end up with this answer. Now, second question, 100 centimeter cubed of 1 molar HCl mixed with 100 centimeter cubes of 1 molar NaOH. So acid and base of equal concentration and equal H plus and OH minus. And the maximum temperature recorded was 26, so that's a 6-degree rise Celsius. And assume density 1 gram centimeter cubed for the solution and 4.2. So 6 degrees Celsius, you just do Q equals mc delta T. So mc delta T. So you multiply 1 gram per centimeter cubed times 200 times 4.2 times 6, and then you do end up with minus 50,400 joules per mole. No, what you get is the energy, and then you have to divide by whatever amount of water is formed. So it's 100 centimeter cubed of 1 molar for both of them, so 0.1 times 1, which ends up being this answer. Now for part B, NaCl is mixed with AgNO3, so they asked to find the temperature, not the temperature, the specific heat capacity. So you can just use Q equals mc delta T, because you have this value, and you have to combine it with AgCl. So the specific heat capacity of the solution is minus 418. So 418 times 1 gram per milliliter. How many milliliters? It's 400 milliliters, because 0.4 liters. And then that's M times C, 4.18, and then times T, the temperature change, so 1.5, all over the number of moles, which is, as you can see, AgCl, Cl, and they have, it's 1-to-1 ratio, and it's present in 1-to-1, so you can just use that. So 0.2 CV times 1, and then you end up with 12540. And keep in mind that since temperature increases, energy is released, so it's always negative if temperature increases. For question 2, part C, you have the exact same scenario, but this time you'll notice that the values have changed. So since the Cl and Ag react in a 1-to-1 ratio, you just pick the one that's smaller. So it's this. So you use this for your calculations. So now it's the exact same thing to find delta H. You do Q minus Q over M, which is equal to minus mc delta T, but since you have density, it's density times volume times C times delta T over This time you take the limiting reagent. So the number of moles, AgCl. So Ag and Cl, it's 1-to-1 ratio again, so 0.1 times 1. And then you answer the question and you end up with 18.8. So for number 3, a 20-gram piece of metal was dropped into calorimeter. So obviously the metal will lose temperature to the water, and the water will gain temperature. So you have to sort of get the energies equal. So the water was stirred and its highest temperature was recorded to be 27.5 and 25 degrees Celsius. So once it was stirred, then we know that their values are equal. Not their values are equal, sorry. That the value of the heat lost of the metal was equal to the heat gained by the water. So you just equate Q. So Q for the metal is mc delta T. So M is 20 grams times C, which you need to find out, and delta T is, it was at 62 degrees Celsius. The water was stirred and recorded to be 27.5. So the net change is 62 minus 27.5. So mc delta T of metal is equal to the Q gained by water. So again, mc delta T 40, mc 4.18, and delta T, which is 27.5. So 27.5 minus 25, which is 2.5, and you just solve this for C. So this is 20 into 62 minus 27.5, and then you just put in the calculator and solve it. You end up with 0.606. 4a, determine the standard enthalpy of formation. So standard enthalpy, it's a few conditions to know if it's that equation. All of the elements must be in its elementary state by itself. So like H over here, it's H2, F2 here. If it was Na, it would be Na alone. If it was carbon, it would be carbon alone, and maybe like salt, you put the state symbol, so like that. The second condition is that it has to be 1 mole of product, 1 mole of the substance produced or formed. So the standard is defined as a change in enthalpy for 1 mole of a compound from its elements in their standard state. So H2, F2, not just H atoms, which are very reactive. Gaseous hydrogen and fluorine. So we have here, that's the formula, because H2 and F2 are the elementary states, and then 1 mole, and then you just balance it. And with an enthalpy change of minus 540 kilojoules. So you need 1 mole, this is 2 moles, so you just divide by 2, and you get minus 270. Divide by 2 equals to minus 270. Now, Hess's law, it's basically just sort of math, I guess. So you need this equation. So let's just work with the reactants first. So Fe2O3, we need 2 of that, but in the other side. So it's 2 times 820. So the negative becomes positive because you flipped it to the other side. Then you need 3C. So this one stays the same, but 3 times. So plus 3 times minus 390. Then you just make sure that every product is sort of cancelled out. So here it's flipped, and you need 2 of this, so 3O2 on the N side. This is very messy right now, but 3O2 on the products because it's flipped, and 3O2 times 3 on the reactants, so they cancel out. And then CO2 is the same for 3O2, and then it's 2Fe times 2, so 4Fe. It's flipped, remember, so it ends up in being in the products. So when you do the math on the calculator, you get this. Same for here. decomposition of B2 H6 into its elements. So decomposition is B2 H6, this is balanced, into 2B plus 3H2. This is basically just making it elements. So B, boron, is a metal, so it will be alone. Hydrogen is a gas, diatomic gas, so it will have two atoms which will be split from the six, will be paired together. So again, B2H6 split into 2B plus 3H2. So you start off with B2H6, so it's just one of that, so it's minus 2100, and then you have next H2 but on the other side, so you need one of that and three of that, but on the other side, so it's minus 3, so plus minus 3 times minus 250. And then you need boron. I'm going in order from up to down. You don't have to. You can just go along the list. So boron, you need it on the product side, and it seems to be already matched with 2. So you just multiply by minus 1. So minus 1 into minus 1250. And then you solve it in the calculator, you'll get the answer. But just to make sure, you should always try to make sure that the products align with the reactants. So minus 3 is 3 over 2 on the product side, 302, and this is 1, so 302 is here, and then minus 1 here is 302, so this adds with the 302 and becomes 3. These cancel, and then 3H2O with 3H2O, they cancel, and B2O3, it's just 1. So
Guys, let's do part number 5, part C. We have 3 reactions. I'm not going to read them out, you can read them. And we have 3 delta H's for each reaction. We need to use the above equations to calculate delta H for the following equation: FeO solid plus CO gas to give Fe solid plus CO2 gas. Now this is Hess's law. I'll give you guys a few seconds, you can solve, and then we'll check together. Okay, let's check it together. First, to make our lives easier, let's call this reaction 1, reaction 2, reaction 3. So, whenever I'm just going to be jumping around between reactions, you guys can keep a track. Okay. Now, this question is a very tricky question, and the way they explain the sheet is correct, but it's a bit misleading. So, let's just see how it works. What we should see here are the ratios. The ratio between FeO and Fe are 1 to 1. So we need a number that, the ratio is 1 to 1. But here we have 3 FeO and 2 Fe. What should be done? Well, you should multiply each number by the other number to get a common factor, or a common multiple, sorry. So what we should do is, since Fe is required on the right side, all you have to do is multiply this by 3. And since FeO is required on the left side, we flip. So let me just write flip. Then multiply by 2. So now I'm working on reaction 3. Okay, reaction 3. Flip, multiply by 2. I have flipped, so 6 FeO. I'm not going to write the states because it's going to take a long time. Plus 2 CO2 to give 2 Fe3O4 plus 2 CO. And when I multiply the second reaction by 3, I should get 3 Fe2O3 plus 9 CO to give, let's see, 6 Fe plus 9 CO2, right? So now we've got 2 reactions out of 3 sorted. All you have to do is work on number 1. Now what should we do on number 1? Let's think about the other reactants, sorry. Now we have, let's see, Fe2O3 and Fe3O4. These two are not needed in a reaction. We have to find a way to cancel. Well, we have 3 Fe2O3 on the left side of the first reaction, and we have 2 Fe3O4 on the right side, both of which are corresponding. So what we need to do is just flip reaction 1. So we are able to cancel everything. So when we flip, we should get, let's see, 2 Fe3O4 plus CO2 to give CO plus 3 Fe2O3. Once we have, let's check now quickly. Okay, 2 Fe3O4, 2 Fe3O4 are cancelable. 3 Fe2O3, 3 Fe2O3 are cancelable. 6 FeO, 6 Fe right side. 2 CO2, okay, we have CO2 here, okay, it works. Now let's find out the delta H's for each of them. Let's start with this, delta H number 3. What did we do? We flipped and then multiply by 2. So minus 2 times this, right? Now let's work on delta H2. All we did was multiply by 3, so it's 3 times negative 22.78. And delta H1, let's work on that. All we did was flip, so it's 50.20. Now we have to add this huge number of equations. We immediately cancel. This is cancelable with this. We have 6 FeO plus. We have 2 CO2 plus 1 CO2 is 3. 3 and 9 on the other side, so 6 will be gone. So these two are cancelled. 9 CO, 2 CO and CO. 9 minus 3 is 6, so 6 CO, we got rid of these to give 6 Fe comes down plus, if we remember, oh wait, Fe is also gone. We had 2 plus 1, 3 minus 9, so that's 6 CO2. Now we finally move on. Let's just quickly write a quick summary of what we had. 6 FeO solid plus 6 CO gas. Let's go back to the states. Plus 6 Fe solid. Oh, sorry. To give 6 Fe solid plus 6 CO2 gas. Now, if we quickly go back to the given question, this is exactly what they required, but they want ratio 1 to 1. And let's just quickly write the delta H. Let's call this reaction 4, which is equal to, if we add them all up, minus 65.04 kilojoules. Now when they want ratio 1 to 1 and every single number is the same, we just divide by 6. So dividing by 6, we should get FeO solid plus CO gas to give Fe solid and CO2 gas. And our delta H4 was this, so all I have to do is divide by 4, so it's minus 6 by 6, sorry, giving us minus 10.84 kilojoules. And that's how you solve number 5, part C.
Okay, so for number 6, you have to find delta H, and you're given sort of delta H of formation. So formation means if they're formed, you use that energy, but if they're broken down, then you just reverse the sign. So O2 is an element. It's in the elemental state, elementary state. So you don't need to worry about it because it's 0. The formation is 0. But C3H8, you have to break it down. So that's why for this, it's the opposite. It's not minus, it's positive. And then CO2 is produced, so, and the coefficient is 3, so multiplied by 3, so 3 minus 390 plus H2 is 4, and it's produced, so it's formed, so just plus 4 times this, and then plus 1 times minus 1 into minus, well, let me make that clear, minus 1 into minus 100, and you simplify it, and you get this. Number 7. Consider a calorimeter of heat capacity. This when part 7, you're asked to find delta H in kilojoules per mole. So the obvious answer is, since it's kilojoules per mole, so energy per mole, so minus Q over M, and then equal, so Q is heat capacity times increase, 5.7, 11.3, you end up with kilojoules, so you don't have to worry about that, times 5.7 over N, so it's 3 milliliters density like that, and then with C2H4. So N is mass over molar mass, and then mass is density times volume, so 3 times 0.789 over the molar mass, which is 28, because C2H, it's not 28, the 28 is for C2H4, but C2H5OH is what we have to calculate. I think that's a mistake over there. Yeah, that's a mistake. So C2H5OH, it's 46. So C2H5OH, and you just simplify that, and you'll get the answer. Okay, so for number 8, we're asked about ionization energy as we move across a period. So you have the nucleus with increasing positive charge as you go from left to right, and you have the same number of electrons, core electrons. So let's say for the first group you have one electron there, one electron. This positive energy is going to reach it from this side, and then this positive energy doesn't reach it. But let's say you have the second nucleus of this is group 1 and this is group 2. So here you have the nucleus, and you have the core electrons, and you have these valence electrons. So as you can notice, you have a higher positive charge but the same level of shielding, so it will attract the electrons more closer, and it will attract it more strongly. Therefore, it's harder to remove them, and ionization energy increases as you move across the group, period. And as we move down across the group, the shielding increases. So here, the first period, and you have, let's say, one shielding, and then second period you have two shielding, and then the valence, and then third period. So as you can see, the electron gets further and further away from the nucleus, and therefore it's less strongly bonded, so it takes less energy, so less ionization energy is required. And arrange the following in terms of ionization energy for size. Nitrogen has the highest, because, and phosphorus has, I'll explain later, and then Si and Al. So as we said, ionization energy increases as you grow across the period, and this is group 3 of the same period, this is group 4, this is group 5, and this is also group 5. So these are the same period, so obviously it makes sense why the increase in ionization energy. And then as we said, across group, as we go down, then ionization energy decreases. But nitrogen is a step up, it's the second period, while this is the third period. So this one, it's closer to the electrons for the same number of valence shell. Yeah, for the same number of valence electrons. So this has a higher ionization energy, and that's why it goes like this. So here, same period. Here, same group but different period. So this takes a higher energy state. Okay, so number 9. Write an equation to illustrate the first and second ionization energy of sodium. So first ionization energy, you're removing one electron from the gaseous state. So that's exactly what happens here. Second ionization energy, you're removing another electron from the first ion that was formed from the first ionization energy. So here you have it. So Na plus in the gaseous state, we will lose an electron to give 2 plus Na2 plus electron, I will use 1. And why is the second greater? Easy, because the nucleus, it has the same level of positive charge, and there's less electrons this time, so it will be strongly attracted. So that's why, since it's more stronger, because there's less, let's say, recipients of the charge, then the ionization energy will be greater. The second ionization energy is around 9 times. Why? Because as you can see, this is a Na nucleus, and then you have 2 core here, and then there's 8 valence electrons, not valence, sorry, other core in the next shell, and then you have 1. So once you remove this, since it's just like a lone pair, not lone pair, lone standing, like alone, and it's further away in the last shell, which is less energy level, which has a lower energy level, the first ionization energy is smaller. Next, you'll have to remove one of these, which is in a greater energy level, which is closer to the nucleus, so it's around 9 times greater, so that's why. Why is the energy of sodium ionization less than lithium? Because sodium has a whole other shell of electrons. So sodium has this, and then 1. But lithium only has this and then 1. The size, they're not scaled, the sizes, but as you can see, there's 1, 2, and 1 only. This is the actual nucleus. The last one is the nucleus. So 1 here, one shell between the valence and the nucleus. Here you have 2 shells. So that's why lithium is strongly bonding this electron. It has a higher bond. So it takes more energy to remove this. Why is ionization energy of sodium less than that magnesium? Same shielding, Mg has higher nuclear charge, so it's pretty obvious. And why is the ionization energy of aluminum? It has to do with p orbitals, because as aluminum, like when the extra electron from the magnesium, where it would have gone, is in the p orbital. So this extra p orbital is actually easier than removing from a complete s orbital. So that's why Al is less than magnesium, because Al has the p orbital. Al's electrons, the first ionization energy, is coming from the p orbital. Why is the ionization energy of oxygen less than that of nitrogen? Because again, like in this case, N has a complete, as a half p orbital, but O has a half p orbital plus 1 more. So since this sort of stops it from being either perfectly half or perfectly full, O has less, because it deals with completing the p orbital from when it was sort of stable in this, not stable, but like relatively stable compared to oxygen. So it tends to have a lower ionization energy because of this extra. So visually you could have seen it here, not in the atom, but in a table. So this is the N for P, orbital, but O has this extra one. So instead of like a uniform distribution, here you have extra electrons, so it is easier to remove it than nitrogen. And number 10, arrange the following in increasing size. Na, Na plus lost an electron, so Na is bigger. Cl minus gained an electron, so Cl minus is bigger. And here, all of them have the same number of electrons, which is 10. So it depends on the positive charge, or how much the nucleus is willing to attract the 10 electrons. So obviously, greatest positive charge will attract it a lot, which means the radius will be smaller, and the size itself will be smaller. So Al is most positive, then Mg, then Na, then the neon, then F minus, then O2 minus, then N minus. As you can see, it's decreasing in charge number. So 3, then 2, then 1, then 0, then minus 1, then minus 2, then minus 3. And F minus, Cl minus, O2 minus, Sr2 plus. So first thing you look at is the actual core electrons. So Br and K krypton and rubidium, strontium, same period, and F minus, O2 minus, same period. So second period, third period, and these are larger periods. So F minus will go first because it attracts it larger from F minus and O2. Same period, of course. So F minus, so greater nuclear charge, less size. O2, then O2 minus, they forgot the O2 over there. So O2 minus then, the same period, but less nuclear charge, so it will attract the electrons less, and it will be more free to go outside and make the size of the atom bigger. Then Cl minus, because it's the third period, and the rest are 4 or 5. The rest are all of them are 4. So Cl minus, and then here it's just decreasing charge. So 2 plus, and then 1 plus, and then 0, and then 1 minus. So less nuclear charge is what gives it these charges. So as it goes here, it's less. So size will be bigger due to less attraction. Okay, so for number 11, you're asked about electron species, electron configuration. And here what we have in front of us is the electron configuration, and to find out how much or what order it is in, you just draw arrows. So here you draw the list, and it goes like that. Okay, so you just keep on going in this direction from left to right of arrows until you've met your electron number. So that would be like 2, 4, and then 10, sorry, and then 12, and then 18, and then 20, and then 30, and then 36, 38, and so on. So that's what you do. And then for A, SE and SE2 minus, you just do that thing, and you look in the periodic table for the amount of protons, atomic number, and then since SE is neutral atom, you just copy that. And then SE2 minus, you just add 2 more electrons. The radius of SE2 minus ion is larger than SE atom because you're adding 2 more electrons, so it additionally becomes bigger, and the positive charge is more, spread out throughout all the electrons, so it's more loose in a sense. So the extra repulsion between the, electrons pushes them away and increases size. Se2 minus ion is isoelectronic, easier to remove electron. Well, that depends on the charge and the electrons and how they interact. So both electrons are from the p orbitals, and because they're all in the same orbitals, because they're isoelectronic, and they're none of the exceptions. And it requires less energy to remove 4p orbital from a selenide ion, simply because it's not its natural state. Se2 minus is an ion where you had to give energy to make it to make the electron free, or to make the electron go to a higher energy level. So this energy spent obviously increases for every electron you remove. So it is no doubt that Kr Se2 minus is easier to remove an electron, and Kr is a neutral atom, and it's noble gas, and therefore it's very stable. So Se2 minus is easier to remove. And it's less attracted to the nucleus because there's more electrons than protons. Number 12, successive ionization energy. This one's very easy. You just check for the biggest jump, and this is around maybe 2 times, and 2 times, and 2 times, and then 2 times, and then here it's a around 5 times jump. So you can tell that it's it's group 5 because 5 valence electrons. And since it's 5 valence electrons, it can form covalent bonds, or it can form ionic bonds with 3. So like group 5, 6, 7, 8. This one's 0, and this one's -1, -2, and -3. So it would form chloride, so YCl3. But there's also a special case where the electrons, you know how it's 5 electrons? Yeah, each of them bonds to a Cl, as we saw in the shapes of chemistry, in which Ali will explain later. So it's YCl3 and YCl5. Yeah, that's the answer. And then number 13, first ionization energy, Al, is less than that of B because more shielding, because Al is here with core electrons, and then another core electrons, and 3 valence. B has 1 and then 3. So less shielding, more closer to the nucleus, and therefore more ionization energy. Ionization energy of F is greater than that of O, because here you have F, O. F has a greater positive charge, and the same shielding is experienced. So even if this has 7, and this has 6, right? It's same shielding, so whichever one has the greater positive charge will attract the electrons more. So therefore F is having a greater first ionization energy. Atomic radius of Ca is larger than that because there are more valence electrons in the higher shell. So like 1, 2, 3, or NMG has only 1 and 2 and 2 valence, and this one has 2 valence as well. So more shielding. So atomic radius is greater, but the ionization energy is less because it's further away. Second ionization energy is greater than the first because obviously the nucleus has a positive charge, so once you remove an electron, it will have a net positive charge, so to remove another electron again from the already positive charge, it's very difficult, and difficult as in it takes a lot of energy. And the atomic radius of Cl is smaller than that of S because Cl has a larger nuclear charge. So it's the same group, Cl, S, same shielding. And this one has 6, and this one has 7. So as you can see, the shielding is the same, but therefore it depends on the nuclear charge. So Cl has a greater nuclear charge, and it attracts it closer. So this is closer, and as it attracts it closer, the size is smaller. So therefore Cl has a smaller size due to its larger nuclear charge. And then number 14, predict the formulae, Mg and M. Mg forms 2+, and N forms 3-. You just switch them. So Mg3, N2. Al, it forms 3+. You look at their groups, and then -2, and then you just switch and switch. So Al2, O3. Li has 1+ ion, and O is 2-. You just put the numbers like that. So Li2O. And then Ca forms 2+ ions, and F forms 1-. So therefore you put 1 down, 2 down. So CaF2. Ca1F2. So you don't put the 1. That's basically what's happening here.
So number 15a. How do the size and charge on ions generally affect the value of the lattice energy? Lattice energy by definition is the formation of one ionic solid from its gaseous ions. because you're forming bonds, you're releasing energy. When you break bonds, you need energy, so you supply this energy. So, but here you're forming bonds, so then again, you are releasing energy. Releasing energy means exothermic, so that's why you can compare the exothermic levels, one being higher than the other. So that's why when you say most exothermic lattice energy, you're referring to the one with the highest lattice energy. So let's take examples of what makes, like what are the factors. The factors are size and charge. You can use Coulomb's law to make the bridge between the lattice energy and the charge and the sizes. So Coulomb's law says that the electric force is directly proportional to the product of the charges and inversely proportional to the distance between them. So in this case, the greater the charge, the stronger the force. So therefore, the stronger the bonds, so the more energy released when you form them, because you need more energy to break them. So that same energy in reverse, you'll be getting more energy to form them, because it's like give and take. So even if you need more energy to break, it just means that you need more energy, that you're gonna get more energy when you form. So yeah, so if the distance, let's say, decreases, again the force increases. So your highest force is the ones with the greatest charge and the smallest distance between them. And because the distance relies on the size of the ion itself, so the smaller the ion, the stronger the bond, the stronger the force, so therefore the more exothermic the lattice energy is. So let's immediately hop into the questions here. So LIF and KF. In here you have the same anion, so you don't look at that. You look at the cation, Li and K. They're both plus plus, so now you look at the sizes. Usually start with the charge. The charge is usually your easiest answer, or the easiest way out. So because the charges now are equivalent, we just look at the size, which is the final factor. Li is much smaller than potassium ion, so therefore immediately LIF is more exothermic. Now NaCl and NaI, again, in this case cations are the same, so anions are what you should be looking for. Cl is smaller than the I, so immediately NaCl is more exothermic. MgO and Na2O, again same anion, so you look at Mg and Na. Here it's Mg2 plus, here it's Na plus, so immediately your charge saved you some time by immediately saying this is, you know, greater charge, so greater lattice energy, more exothermic lattice energy, so that's your answer, more exothermic lattice energy than the Na2O. So CaO and CaOH2, same cation, you look at O and OH minus, this is O2 minus, this is OH minus. Even if you have two, you're still talking about, like, you're comparing them individually. So that's why, then again, the CaO is more exothermic than the other one. So in number 16, we are using the Bourne-Haber cycle to calculate the lattice energy of NaF, and we're given some reaction energies over here. So let's start. The easiest way to start is to start with the solid itself. We can, to be honest, you can start from anywhere, but I highly advise you start from this step. You have two reactions that produce this species over here, the solid. The first one having the energy called lattice energy, and the second one having its energy called standard enthalpy of formation, or the enthalpy of formation, so delta H F. The first one is forming the ionic solid from its gaseous ions, so that will be Na plus gas plus F minus gas. This one is forming the ionic solid from its, or like 1 mole of that solid from its elements in their standard state. I was recalling it from memory, that's why I paused. So here you have F, and this is by nature diatomic because from their elements, and this is gas, again by nature. These are all reactions, by the way, so they are reactions with their energies. So, and every reaction must be balanced, so this is why you put half. So let's keep on going. So we're supposed to reach this, but we're gonna do it in a series of steps. So let's continue, step at a time. Let's start with the Na. We cannot ionize immediately to reach this, so we have to change into gas. So what we want is Na gas plus F to keep everything the same when you change something. When you change a single factor, you keep everything the same. Okay, so solid to gas, that's atomization, also called sublimation. So delta H atomization, or however you want to represent it, also sublimation, same thing. And then you go, now we can ionize immediately. Na plus gas plus half F2 gas. This is called the first ionization energy of sodium. And then we keep on going. This time we're done with the sodium. If you look carefully, we have Na plus gas, Na plus gas. We cannot do anything to the sodium because that's how we want it to be. So we want to reach from half F2 to F minus. So for the F2, which is F bonded to an F, we want to reach F and an F, which make a 2F. So to do that, we have to break the bond, and this is called the dissociation, or the bond dissociation energy. And that's defined by nature to be the breaking of 1 mole of bonds. However, do we have 1 mole? No, we have half. So this is not dE. This is dE over 2. But let's write. So it will be giving us by nature 2F, right? But we already have a half. But let me write it. It's fine. Let me write it. Let me write the entire thing. Na plus gas. This is what I meant. Look, you will be having half times 2F gaseous, and then of course half with 2. So that's what I meant earlier. So you can immediately just write F gas. And then from this step to this step, Na plus gas, same thing. Here you're changing from the fluorine gas into a fluoride ion in the gaseous state. In this case, you are giving an electron, so this is not ionization energy, this is electron affinity. So there you have it. We are done with the ionization, we're done with the Bourne-Haber cycle in this part. Now all you have to do is just add the energies. So you pick a direction, you pick for example this, clockwise, and start from somewhere. To be honest, start from this, safest and the best, but to be honest you can start from anywhere. And then again, it's just conventions. The conventions are there to make your life easier. So let's continue. So we go from here all the way there. So delta HF is on the other direction, so you have to do minus. So minus delta HF. Atomization is with it, so plus delta H atomization. I'm just gonna say it atom. And also keep in mind the balancing. If you have something like Mg2 plus, you have to be aware that you have to do the ionization energy again, and there are some stuff that you might end up needing to balance, especially when you have, let's say, MgF2 for example. You have an F2 over here, things that change slightly, and you might have to do certain stuff more than once. So yeah, so again, atomization and energy, ionization energy, same direction, i.e. first one, plus, from memory I think, yeah, plus, yeah, it's plus, and it's dE over 2. I'm writing quickly, not to waste time, and then EA, electron affinity, with the direction of the arrow we have over here, and then finally the lattice energy, again with our direction. All of this is equal to 0 because you're starting from a point and you're ending at it, so of course the sum of the energies should be 0. So we have finally this equation. So you basically just sort and you calculate. If you want me to do that, let me do it quickly. So we want the lattice energy, so everything will be taken on the other side. To do that, you just negate this, negate this, negate this. By the way, I'm doing LE equals minus. Actually, let me do it with you. It will be delta HF minus delta H atomization minus IE1 minus TE over 2 minus EA, and we are done because we just took LE to the other side. Pretty much. So let's just calculate. So we're given the values. So just put the numbers. HF, that's minus 570. Also, you have minuses sometimes from the energies, and you of course have the minus from the formulas. So just keep that in mind. So if you ever see a minus, you might end up with a minus minus. So just type that correctly in the calculator. So minus 570 minus the atomization, where is it? Yeah, 109 minus lattice energy. Sorry, the ionization energy 495 minus D over 2, 154 over 2, and finally minus the electron affinity, which is already minus, so I'm gonna write plus 328. We get negative or minus 923 kilojoules per mole, because after all we're subtracting, so it will take the same unit, and we're done pretty much. If you have ever found some difficulties in, either recalling or coming up with an answer to the question, are broken bonds exo or endo, are formed bonds endo or exo, and is delta H with respect to broken and formed bonds, is it broken minus formed or formed minus broken? If you ever find difficulty in remembering it, like for example on the spot, because every time you need to be reminded of it, then this should in some way help you. Even if it doesn't help you remember, it will help you to reform or recreate the formulas and the answers in your head, so you'll be able to answer yourself without the need of memorizing it, if you still recall the analogy at least in your head. So we have here broken bonds. Logically, when you have a bond over here and you want to break it, you're going to have to apply some force on it. Imagine, let's say you have a door. To break a door, you're going to use so much force just to break it. And this force, of course, comes with energy. The same thing, to break a bond, you need heat in this case, and this is supplied energy. When you're supplying energy, it's endo, which is by definition positive. And we're doing this, we're breaking the CLs. And if you want to do the opposite, which is again by default should be negative, this is the formation of the bonds. You're forming bonds, and we just wrote, because it's the opposite of this, it should be the opposite in sign also. So if this is positive, then this is negative. So even if you don't see the connection between forming bonds and releasing energy, at least you can see it as the negation or the opposite of breaking a bond, which logically should connect with supplying energy, which means endothermic. So this way, if you forget one, you can get the other. Usually this will be your reference, because then again, if you're unable to see why forming bonds releases energy, you should be able to see why breaking bonds, energy is needed to break bonds. So we're done with this, so we can prove this, delta H itself. So we said this is endo. Breaking a bond means supplying energy, so endo. Endo is by nature positive. Forming a bond, however, we said it's opposite, so negative. And this is actually where the minus comes from. It's actually originally the summation, and then the summation itself has a minus. A plus minus is what is minus, and this is why you have a minus. So this way, we just proved how you can get the delta H, and individually, if you were asked which one is endo, which one is exo, or individually, then you know what to say, you know what to do. So let's now get away from the formula. We have it in mind. Even if we forget, we can remake the formula again. So what was delta H? We said breaking a bond means you supply energy, so it should be kept the same. So I'm gonna say bonds broken minus bonds formed. Okay, so for this one, the broken ones are the reactants here, because you're gonna break this and that and that and that to form these. So it will be N triple bond N, the energy of that, plus the energy of, there are 3 HH bonds, so you have to break 3 HH bonds. Of course, make sure it's balanced, and here it's balanced. It will be easier if you can't see the balancing here, you can balance from here, and these would be the same technically, so you can just immediately do it, or faster. And here you have 3, and here you have 3, so you have 6 of the NH bonds. So basically this is the bonds broken, these are the bonds formed, so you subtract the energies of these two. So this is minus that. So let's put the numbers immediately. This is 9, 4, 1 plus 3 and 2. 4, 3, 2, which is over here. And then minus 6 into NH, which is 3, 9, 1. And you get 9, 4, 1. Let me just put that. 9, 4, 1 plus 3 into 4, 3, 2 minus 6 into 9, 3, 9, 1. You get minus 109. Minus 109 kilojoules, pretty much kilojoules. So we're done. So this one, the easiest way to do it is, like immediately using your memory. O, H, H, 2 electrons, and then done. This is bent, V shape, angular, the name of the structure, and then you have ammonia, which is like this, and then you have a pair of electrons. If you want to double check, you can do this. Nitrogen has 5 electrons, it's sharing 1 with each hydrogen, it's left with a lone pair, pretty much. This is called triangular pyramidal. And if you want to show the wedges, you can go like this, like that. You can pick any, you can pick even the ones where you go like this. What anyways. Yeah. CCl4, carbon has 4 electrons, sharing 1 with each chlorine, but again from memory you can just go like this, boom, like that, and you're done. Of course you're left with the electrons here, just like this. If you count, you should have the correct number of electrons. And if you want to put the wedges, it has 4 atoms, and from the way it is, you have again horrible, but anyways, it's square pyramidal. Let's keep going. And then you have N triple bonded to another N, you have a lone pair of electrons, you're done. Oxygen double bonded to another oxygen, and you have the electrons here. Now if you want to double check and you forgot how to, just basically count the number of electrons. If you have an N2, you basically have a 7, or 2 times 7, because each nitrogen has 7 electrons. Sorry, my bad, 5, my bad. So 2 times 5, you'll end up with 10 electrons. So that will be, if you're doing it step by step, if you put the full set, the octet rule, basically you're satisfying the octet rule, and you count, you have 6, 6, so that's 12, 12 plus 2, that's 14. You want to bring it down, 4 electrons down. Adding a single bond takes away 2 electrons by calculation, because you're taking 2 from each side, so you have a net decrease of 2 electrons. So you can just immediately add another third bond if you know your math. So you can immediately go like this and take out those 2, take out those 2, take out those 2, and take out those 2. It's fine if you don't understand this, you can just immediately go like nitrogen, 14 electrons we said, right? 14. So again, I'm just drawing the arrow to show you, it's not some reaction arrow, it's just me writing. Let me do this. Okay, and then you have a double bond, and you're removing 2 electrons. Let's remove these, for example. And then you go again, triple bond, you're left with this, pretty much. And yeah, that's pretty much how to do the nitrogen. Same thing with the other ones, same thing, calculate, and pretty much you can do everything. This is linear, and this is linear, and yeah, pretty much. For this one, usually it comes with practice. You know which ones are right, which ones are not. And there are, by the way, there are other ways to know. For example, when you have NO+, you can do the calculation, and you can do the thing, and it will not take you time, but you can do this. N2 is very, very, very close to this. The only thing you have is you have an oxygen which has 1 more electron than another nitrogen, because if you have 2 nitrogens, each one having 5, so that's 10. But if you have an oxygen which has 1 more electron, you'll end up with 11, but you also have a +1 over here, so it will be -1 electron because you're taking it away, so you have 10 again. So these should have the same structure as the nitrogen triple bond nitrogen. So they should look something like this. See, of course you have to do this and then plus, and you're pretty much done. You can do the rest same way. The CN, one special way to do it is, I guess, not really sure about I mean, you can do it, yeah, NN again, NN, and C has one less electron. Yeah, one less electron, but you have a minus, so you're adding that electron, so you're back to square one, like this. So yeah, pretty much. And then you can just keep doing the rest. But here, you can remember it like this: boron species have or like are electron deficient. So immediately this is not following the octet rule. Electron deficient means when you do this, they're gonna look like this. Like the boron will not need to have the octet rule satisfied for it. It will be the one that says it's fine, I don't need. It will be the ones that will kind of like give the compromise. It won't like complain about this not having the electrons. It's electron deficient, so it's fine. It's fine with just feeling 6 around it. For the other exceptions, you'll have ones like this and this. These two are because they can extend their valence shell, so they will have like this. The PCl5 will have something like this. Cl, 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 Cl. Let me draw it a bit bent, just because it looks nicer and probably more correct. Like this. And you just, it will take time, but like you just go like this. If you once you're done with this, and you can double check with the calculation, phosphorus having 5 electrons. By the way, I might say something wrong because okay, let me just do this. Okay, so 5 electrons, and each Cl, so that's 5 times 7 plus 5. So that gives you 35 plus 5, that gives you 40 electrons. You have 6 on each chlorine, so that's 6 times 5. You have 30. And you have 5 bonds, each one having 2 electrons, sorry. So you have 2 times 5, so you'll have 40. You're pretty much done. But here you have the anomaly, which is first of all, phosphorus is making 5 bonds, so that makes 10 electrons. So therefore you just have an exception, extending its valence shell. Phosphorus compounds can do these, sulfur compounds can do these, and the I3 minus, if you do the same thing, you notice that there's something off with it. If you do it normally, like this, for example, like this, and count, each I is I minus, so you have group 7, so 7 electrons times 3, that gives 21. You add one more because it's an ion over here, it's an anion, so you have 22, or negatively charged, 22. So 22 electrons. Let's calculate this manually. You have 6, so that's 12. Actually, an easier way to calculate would just be like 8 plus 4. So 8 times 2, which is 16, plus 4, that gives you 20. So 20 electrons. So basically you have 22, but you're using 20, so you just add another set of 2 electrons. Then again, look what you have. You have 3 lone pairs, and you have 2 bonds. So it makes 10 electrons around the I atom. Whoops. 10 electrons around the I atom. Then again, another exception, and you can keep going with the rest in the same way. So the ones that would be the exception would be not these, the boron compound, and you have the SF6, PCl5, I3 minus. The xenon will have a normal structure with the lone pairs normally. Let's check the ICl4. I'm expecting it, I'm positively expecting that it again doesn't follow the rule because we have I. So let's see how we're gonna do this. For me, by default, I'm gonna start with this immediately because I know that the structure is going to be correct in the end. So you have I, which is 7, plus again Cl, which is again 7. So 5 times 7 plus 1, you have 36. Because this one has 7 electrons, and each of those have 7. So you have 5 times 7, and you have minus, so plus 1, you get 36 electrons. If you fill the octet rule, which is going to take me time to draw everything, but if you do it on your own, you'll end up with 6 on each chlorine, which I'm done with right now. 6 on each chlorine, so that's 6 times what? 6 times 4. Plus, there are 4 bonds, so that's plus 8 electrons. You have 32. 32! So how can you go 4 electrons? It's basically asking you to do this. Add a pair and another, and you're done. There you go. 2 lone pairs, 4 bonds, another exception. So that's it pretty much. So the rules in general are boron compounds being electron deficient, the the sulfur compounds and the phosphorus compounds that could form or that could extend their valence shell. Also, always draw the Lewis structure before, like if you're unsure of these, you can confirm, because sometimes you can have the compounds being normal, like with the actual proper amounts. Depends on what kind of combination you have. And then the I3 again could extend their valence shell, as we have seen in this example and this example. And yeah, pretty much. So for the resonance structures, you just do them normally, like like you do the Lewis structure normally, and then you do something special towards the end. So normally 5 plus 3 into 6 electrons plus 1, giving you 24 electrons. So you draw it like this, N, O, O, and O. If you put the electrons, you're gonna end up with 26. If you want to double check, let's double check together. So you have 6 around each oxygen, so that's 6 times 3, because there are 3 of them, so 3, and times 6 because each one has 6, and this is having 8, so plus 8, that you will get 26. 26 is 2 electrons higher or greater than 24, meaning that I have to reduce by 2, meaning forming a double bond. So in this case, you can form a double bond here and erase those 2 electrons and erase those 2 electrons, and you're done with NO3 minus 1 structure of it. Because you have a double bond, there's the possibility of forming a double bond here, and there's the possibility of forming the double bond also there. So you'll end up with another structure, again same thing, except that you have the double bond here and the O's like this. And minus, and again a third structure. Same thing, but like this time with the double bond being here. And these of course would resonate to give us a more accurate structure, or like we represent it like this: O, O, and O. This is basically saying I have somewhat a single bond and a double bond, but to be accurate, it's not a 1.5 because this bond is resonating 3 times, and resonating 3 times means it's 1/3 stronger than a single bond. So this is 1.3 stronger than a single bond, because you have it resonating here, resonating there, and there. Like the electrons are just like this basically. So yeah. So yeah, pretty much. For the rest, same way, NO2 minus, you're gonna end up with N, and then O, and another O. You pick the double bond here, for example, you end up with this, and it's minus, right? NO2 minus. So you'll have it like this, and then of course the resonating structure would have the double bond on the other side, like this. And like that. And we're done pretty much. The rest follow the same manner. CO32 minus, again you calculate, you put the electrons, you know, satisfy the octet rule, and then double check, recount, and then do the necessary formations or changes or amendments. You're probably gonna do just a double bond here, and you're gonna pretty much notice that you have three atoms, so 3 possible resonating structures. SO2, same thing as NO2 minus. You're gonna have a double bond on one of the O's, another structure is on the other O. Same concept, same way. If you know one of them, you know the rest. So for number 21, we're using this one theory called the VS-EPR theory, which stands for the valence shell electron pair repulsion. And this is basically having the repulsions between the lone pair, shared pair of electrons or electron domains being stronger than the shared pair and shared pair repulsions. So here I've drawn a small tiny diagram of the molecule of a water molecule. If you were to imagine this repulsive force between this lone pair and this shared pair, this is like, if you consider, let's say, both lone pairs, so these repulsive forces are going to be stronger than these repulsive forces between the shared pairs themselves. Because they're stronger, you're going to end up pushing them until they're so close to each other, or they are not so close, actually at a distance from each other, that the forces basically balance out, and you have a smaller angle, a new one that's stable but a smaller one, which will end up being 104.5, the actual angle of water in this case. This is due to something that the VS-EPR is built on, which is the lone pair, shared pair electron repulsions being greater than shared pair. Thus, you're overriding the shared pair repulsion effect. You're overriding it because you're winning over it. So you're pushing the electrons until you reach, of course, a stronger force, and then they reach equilibrium. So the classification of this is AX2E2. We're expecting an AX. Well, the expected shape is the AX4, which is the tetrahedral with a bond angle of 109.5. But instead, we're getting, of course, an AX2E2 because of, or due to the VS-EPR, or at least the VS-EPR could, like, it can explain it, and it says that you, or like as a result, you'll have a smaller bond angle. So if you were to consider, let's say, here without the lone pairs, but of course, to correct this, I'm not going to have a specific one, just to be accurate. Yeah, A, X, 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 X. You're going to have a tetrahedral of bond angle 109.5, but of course in water we have 109.5. If I said 4, sorry. And here you're going to have instead 104.5 because of the repulsions, you know, from here. So if we consider the PCl5, which we have over here, one quick way to do it is basically phosphorus having 5 electrons, right? And chlorine having 7. They only need 1. Phosphorus has 5, and there are 5 Cls, and each Cl wants 1. So you give it, or you share basically 1, not give. You share 1, and that pretty much gives you the shape. No other modifications to it. No adding, no subtracting, no nothing. And we're done with this. So you could do this and apply this way to the other ones. For example, let's jump to xenon. Xenon, let's do xenon over here. Xenon, fluor. Okay, so we have an XC and 2 Fs, and if you can immediately start calculating, but if you use my way, you have 8 electrons over here, and the fluorines need 1 each, so you're gonna share 2. You're sharing from the xenon 1 here, and you're sharing 1 here. You're left with 6 electrons. So how are you gonna put these 6? You just put them like this. And of course you have these electrons by default, octet rule. Aslan, without the octet rule, to be honest, without the octet rule, they are already 7 electrons with fluorine. They're sharing 1 here, and they already have 6, other than the 1 shared here, which makes it 7. But anyways, and of course, wait, did that? Oh, so sorry, my bad. I don't know why I did this. I did it unintentionally. No need for the brackets, of course, because you don't have a charge over here. And then just add, if you want to double check, it's 8 plus 2 times 7, 22 electrons. Let's add 6 plus 6, which is 6 times 2, plus you have 10, 22 again. And this shape has a classification of A, X, 2, the shared domains, shared electron domains, and you have the E, you have 3 of them. And this shape would be linear. This is a linear shape. And of course we can keep on going, the SF and so on and so forth, but to be honest, this is the fastest way, as you have seen. Like, let me try doing IF4 minus quickly. I has 7 electrons, and the F's need 1 each. You have 4 F's, so you're going to give, or share, sorry, why am I saying give again? You're going to share 1 for each. You have 4, so you subtract 4, you end up with 3 electrons. So it's sharing 1 with each fluorine. There are 4, so 7 minus 4, you get 3. You have minus 1, so it's, it's IF4 minus. And because of the minus, you're going to add 1 electron, so you're going to end up with 4. So you have 2 pairs of electrons, because each pair is 2 electrons. So as a result, you're going to end up with something like this. 2 pairs, and F, and of course you can do this and that. But anyways, this shape is called the seesaw because it looks like a seesaw, that shape. So and yeah, you can double check the electrons if you want. Of course, sorry, these electrons, I'm usually not drawing them because in this example, when I'm explaining, it takes time, it's time consuming, and I'm thinking about the explanation as I speak, so that's why I usually forget them. I apologize. Here you have 10 plus 6 times how many fluorines? There are 4, so 6 times 4, you get 34 electrons. 34 electrons. So this is 36 electrons, 36 over here, and we have 36 over here. They calculated 36. They match, so this is the correct diagram. And this is a seesaw again. And the rest, of course, follow the same way. And yeah, pretty much. Whenever we mention electronegativity, to answer, for example, part A, to define it, we usually mention slightly positive, slightly negative, like whenever we would discuss these kind of concepts. We also talk about the shift in cloud, the electron cloud. Why is that though? It's because one attracts, a certain atom attracts the electrons more than the other. So that's why you have a slight shift. Now this brings us back to electronegativity. So let's define electronegativity. It's the measure of the attraction or the ability of an atom to attract electrons in a covalent bond. This is the definition of electronegativity. Part B, what is the trend? Well, the trend is across a period, electronegativity increases, evident by, literally the entire period, but if you want to select a few, N, O, F. N less than O less than F, F being the most electronegative because, across a period, electronegativity increases, and down a group it decreases. Example is Cl and F, for example. These are in the same group, however F is above Cl, and thus it's more electronegative than it. And of course we already mentioned F is the most electronegative actually in the entire periodic table, so there you have it, immediately your answer. So increases across a period, decreases down a group. C, bond, when is it considered polar? Well, when we're talking about electronegativity, which is one of the basics for a polar bond or polar compounds, then we're going to consider a certain number, which is the difference in electronegativity between the atoms. So we're going to take a range about 0.4 to 2. So from 0.4 to 2. If it's within that range, it's considered polar. And here we can arrange HH, SH, CLH. This one's the most polar because it has the highest electronegativity difference, followed by SH, followed by HH, and then you have HF. Immediately with the F, the most electronegative, and H, immediately that's your answer, first one, then HO, then HH. Here, even though you have FF, it's the same atom. We're talking about electronegativity difference, and here we do not have a difference, so this is the least, we leave it aside. We have NF and HF. This N is electronegative, one of the most electronegative ones, the most being NOF. So you have a smaller difference than the HF, so that's why you have this being more polar than this and more polar than that. And we're pretty much done. The atom minus the number of lone electrons minus half of the shared electrons. And of course we'd have to do this again and again for each different atom. So here, like with different bonding, for example this in here, these two will have different formal charges, so you have to do each one separately, but you already know this, so yeah. So the formal charge of the oxygen in the first one, A, is oxygen has 6, so 6, like by default, you know, oxygen has 6, so 6 minus, in this case you have 6 lone electrons, so minus 6, minus it's bonding to one, it has one bond, each bond having 2 electrons, so minus 2 over 2, because in the formula that's with half. So that's 6 minus 6, 0, and then minus 1, so yeah, minus 1. Formal charge, this is A. Formal charge of the sulfur is, sulfur by default has 6, so 6 minus, and it has no lone electrons, minus it's bonding 4 times, or with 4 single bonds, so that's 4 over 2, no, 8, we're talking about electrons, 8 over 2, so 6 minus 4, that's plus 2. So here we have a minus 1, let me just fix it. Here we have a minus 1, and here we have a plus 2. The total charge, if you want to double check your calculations, for example, the total charge would be this times 4, because you have 4 of those oxygens, so you'll have minus 4, and you have here plus 2. Add them, you get minus 2. And now, is the total charge minus 2? Yeah, it is. So we're correct. So let's keep on going. The next one, formal charge of, for me, I'm gonna denote it with O double bond. I'm not sure if this is even valid, but for me, for the sake of the example, I'm just going to define it like this, the notation. Yeah, okay. So it has, how many electrons does it have? The oxygen has 6 by default as a free atom, minus how many lone pairs or lone electrons it has? It has 4, so minus 4. Bonds 2 times, so 2 times 2, because you have 2 electrons in each bond, so that's 4, and it's already half in the equation itself, in the original one. That's 6 minus 4, that's 2, 2 minus 2, that's 0. Formal charge on the oxygen, the one single bonding, will be 6 again, minus, look here, it says it has 6 lone electrons, minus bonds once, so it has 2 electrons over 2, you end up with minus 1. The formal charge of the sulfur would be 6 minus, in this case you have 5 bonds, so keep that in mind. So here you have 6 minus no free electrons, sorry, lone pairs, minus here you have 5 bonds, so it's 10 over 2, so that'll be 5, so 6 minus 5, that will be plus 1, 6 minus 5. And here of course you multiply by 4, and no, not by 4, because you have one double bond, so you multiply by 3, gives you minus 3, and this one's 0, and this one's plus 1, add them, you get minus 2. Again, we're right. Let's keep on going. Third one, you have 2 double bonds, so F, 2 of those, So when we do actually one of them, the formal charge of O double bond, we'll be doing 2, and then the other 2, you know, same way. So you have 6 minus lone electrons 4 minus, you have 2 bonds, so you have 4, so 4 over 2, you have 0 again. Same way actually, to be honest, and you just, to be honest, they are the same. They are the same pretty much. You don't change. 6 minus, again having 6 electrons, minus it bonds once, so 2 2, so minus 1, and then the sulfur, formal charge of the sulfur is 6 electrons, has 0 lone pairs, minus this one is special, it has 6 bonds, so 12 over 2, making 6 minus 6 making 0, and I can already see this is pretty much the lowest. Let's zoom out just to see. So these are all of them. Yeah, these are all of them. This one has the double bond and the single bond. Yeah, this one is the latest one, other than the one we just finished. So minus 1 plus 1. This one is way higher. We already have plus 2, so ignore. Minus 1 plus 1. And over here we have 0 0 minus 1. This one is better. So C is the best so far. So let's keep on going. Below are the Lewis structures for blah blah. Predict the most probable one. So same way, in the same manner. So you have H, C, triple bond, N, O. Actually, I don't need to draw it, just immediately. Form a charge of, in this case you have to do each one. So hydrogen would be 1 minus 0, no lone pairs, minus it's bonding with, it has 1 bond, so 2 over 2, so that'll be 0. And then formal charge of the carbon, that will be 4 minus, here you have no lone pairs, so 0, minus you have 4 bonds, so that's 8 over 2, you end up with 0 again. Formal charge of the nitrogen has by default 5 electrons, minus lone pairs has 0, minus it's bonding 4 times again, so 8 2, this is 5 minus 4, this is plus 1, and the formal charge finally of the oxygen is 6 minus, has 6 lone electrons and minus bonds once, so 2 over 2, you get minus 1. Formal charge, total charge I mean, 0, which is what we are expecting. Formal charge of hydrogen, nothing to change, same here, same one, also 0. This one is different. Let's do the carbon. Formal charge of the carbon has 4 minus 2 this time, 2 lone electrons, minus it bonds only 3 times, so that makes 6 over 2. So that's 4 minus 2 minus 3, which gives you a minus 1. And then you have a formal charge of nitrogen, again having 5 minus bonds, no, first of all the lone, you have 0, minus bonds 4 times, so 4 times 8, so that's 4 times 2 I mean, that's 8 over 2, again 4, 5 minus 4, that's plus 1. And then you have of oxygen 6. I can already see the answer to this, to be honest, but let's keep on going. 4 minus it bonds 2 times, so that's 4 over 2, and you end up with 0. It honestly, to me, it doesn't make sense why the carbon would be more would have the negative rather than the or have the electron over the oxygen, which makes this structure more valid than the other one, even though they have the same numbers, 0 minus 1 plus 1 0, and 0 0 plus 1 minus 1, same thing. The only difference is that the oxygen would make more sense to have the negative over the other one, and thus that's why it's better. So number 24, I really like this one, it's really easy. So they're asking for the optimum wavelength For this one, you immediately can go like it's the peak, and the peak looks like it's 510, so you're done. If you want to actually get the how do you reach the 510, it's 480 till 520, it's somewhere in the middle, so we go with the midpoint. You get 500, yeah, 500 exactly. However, if you go with the 500, it looks like it's midway between the 500 and the 520. So add the two again, divide by 2, you get 510. And we found the peak. Do you use this or this? They're the same. They're the same. They're just reflections of each other, because you're taking another factor which is the opposite, like it reacts oppositely to it. Rather than increases, it decreases, rather it decreases, it increases. So that's all about it. Here we're given the absorbance, and we're looking for the for the number of moles. To get the number of moles, we need the volume. We're given the volume, and we need the concentration, and that's what we're looking for using the graph. So we have an absorbance of 0.275. They already drew the line for you. It goes down here and then goes perfectly on 0.05. So it goes perfectly on 0.050 molar. That's the concentration. We have a volume of 20 milliliter. We need number of moles, which only could happen with SI units. That's why we change on the spot. And then multiply NSCV. You get 0.05 times times 20, times the power of minus 3. So 0.050 times 20 times the power of minus 3. You get 1.0 times 10 to the power of minus 3. And that's the number of moles, basically. And yeah. So the hybridization of these following molecules, you have methane. So you draw the Lewis structure like this, and you count the number of sigma bonds. Each single bond is a sigma bond, so you have 4 plus lone pairs, you have 0, so you have 4, and then you just subtract by 1 by default, so that you get the superscript of the P, because you already have an S, so you're only left with one number minus 1. So that's why you do 4 minus 1, you get 3. And this one, look at it, it's a tetrahedral, with bond angle 109.5. And here we have the second example, the BeCl2, and then you put the electrons here, and then it's sp. Here you have a sigma bond, here you have a sigma bond, so that's sp1, because 2 plus 0, because there are no lone pairs, minus 1 by default, you get 1, so sp1, so sp. And its shape is, as you can see, it's linear, and you have the bond angle to be 180. Let's keep on going. You have H2O, and with this you have 2 sigma bonds, and considering the lone pairs as sigma bonds, you get 4. I mean, we said we add the lone pairs, so we just did that. So you have 4 minus 1, you get 3, so sp3. In this case it's bent, V-shaped or angular. The expected angle is less than 109.5 and less than 107.5, because that's for the one before, the one with the 1 lone pair. Here we have 2, so it's less, so 104.5. And then ammonia and a lone pair. This one is going to have 1 sigma, 1 sigma, 1 sigma. We are considering this as a sigma bond, so we have 4 minus 1, you get 3, so you get sp3. This is this is a trigonal pyramidal trigonal pyramidal, with a bond angle of 107 nearly. The 107 comes from being less than 109.5 and bigger than 104.5 because that's for H2O or H2O with 2 lone pairs. And we continue. Last one, no, not last one. You have still BF3, electron deficient, because you're talking about borons, so you don't even have to consider in this case the boron. And with that we are left with 3 sigma bonds. You have 3, so that's sp2 because it's 3 minus 1, and sp2 here is trigonal, but this time it's not pyramidal, it's not 3D, it's planar. And lastly we have the CO1, which looks like this, but let's say you don't know. Add octet rule, count 6 times 2 and then plus 2, that's 14 electrons. How much do we have? 4 plus 6, we have 10 electrons. So we want to reach this. We have 10, but we are using 14, so triple bond, cancel 2, you get this pretty much. And with that the hybridization is 1 sigma 2 pi's. I mean it's pi, but I'm writing 2 pi. Usually sigma, let's say, is in the middle, and you have pi, and here if you're considering the carbon, which I think is the case here, you are going to say that it has a lone pair, so immediately you say 1, because there's 1 sigma bond, plus lone pair, that's 1, and they both actually have the same answer because they're both 1 plus 1. I guess that's why they never ask about 1 specifically, because they both give the same answer. So 1 plus 1, they get 2, minus 1, you get 1, so SP. 1 plus 1 gives you the number of sigma bonds with the assumed lone pair bonds, minus 1 because that's how things work, because you're already using an S, so it's subtracted by 1, so you're left with an SP shape, linear, bond angle, expected bond angle is 180, pretty much. For this one, the one that's bonded to 3 hydrogens and 1 carbon has an SP of 3, because you have 1 sigma, 2 sigmas, 3, 4 sigmas, so SP3. Now the second one has 1 sigma, 1 pi, 1 sigma, 1 sigma, so that's 3 sigma, 1 pi. You don't care about the pi's, you are left with 3 sigmas, so that's minus 1, you get SP2. So SP3 and SP2, and there's no SP, so it's I and triple I. So we're asked to draw the Lewis structures. These are the Lewis structures. Here you have, let's take out those ones. Here you have like that. This is the ethane, so on and so forth. And these are the Lewis structures. You have the shape of this one. The shape would be, looks like a tetrahedral. So you have 2 tetrahedrals fused. And then this one would be the trigonal planar, 2 of those fused, and here you have automatically linear. Now the SPs, they asked about it in the next one, the hybrid orbitals. The hybrid orbital of this one, both C's experience the same kind of hybridization. So you'll have sp3 because you have 4 sigma bonds, each one's like sigma, 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 sigma. So that's 4 minus 1, you get 3. The next one is sp2. Why? Because you have a double bond, one is pi, one is sigma, and you have 3 sigmas, so you have 3 minus 1, so sp2. And then this one is linear. Why? Because you have a pi and a sigma, so 2 plus 1, no, sorry, minus 1, because we're done adding the lone pairs which don't exist in the first place, and the sigma bonds, you get a total of 2. Minus 1, you get 1. So sp. Polar bonds, they're all polar, because is there an electronegativity difference between C and H? Yes. Between C and H again? Yes. Between C and H again? Yes. So these are polar. Now, polar molecule is different. What about the net dipole? We would say the net dipole is 0 in this case. So they are 0 because the dipoles cancel each other. But of course, you also have to keep in mind these are 3D structures, so not everything applies the entirety of the case. Sometimes they are polar and you actually consider them polar. So we're done with chemistry. I hope you have benefited from this, and good luck in your exam.